All right. So, welcome back. It's 1:05 and we're going to get started. Ooh. All right. Try something like that. Just let me know if the noise is too much or not enough. So today is February 10th. We're going to continue talking about encapsulation and perhaps get to linked lists. You should have submitted your tutorial 4 and tutorial 5 is due like this weekend-ish, right? So I know it's a busy week, so if anybody needs an extra day or two, just let me know. I don't, I'll leave it until somebody asks because, I don't want to get carried away with pushing the date back because then, I don't know, things start to become disorganized, and then I like to keep things, week by week to keep the topics sort of consistent. But yeah, a day or two, especially at the break, is not a problem. All right. So questions before we pick up where we were last class? All right. So last class we were talking about encapsulation, which is in some sense how we protect our objects, right? Or at least one of the ways that we do it. And in particular, we were talking about const. So we talked about how to initialize an object that is statically allocated within another object. So we had a student, and then we had an address that was statically allocated, and that address you needed to call the constructor. If it didn't have a default constructor, then we have a problem. You have in the student constructor, you need to explicitly pass in some parameters for the non-default constructor of address, right? So that's where the solution to that was, of course, member initializer syntax. So if I had a constructor student, after the argument list, I would put colon, and then I would, pass in some of the values, I guess. Assuming I had some parameters here, I could pass them into the constructor of my address, right? So that's member initializer syntax. So we talked about that. Then we talked about, well, what if address was not statically allocated, but dynamically allocated on the heap? And then what we had there was, well, we had to make a destructor and we had to make a copy constructor, right? Because now we have dynamic memory, and so what that generally means is that we want to make a deep copy in our copy constructor. It doesn't have to be that way. You can obviously go with a shallow copy if that fits your needs, but for the most part, you probably want a deep copy. And then we started talking about const. Just variables. And then we talked about const objects. So if I make my object const, that means the member variables cannot be changed, right? That's what it means. But there are certain consequences to that, and one of them is that, well, I can no longer call a function unless I promise the compiler that I will not make any changes in that function. Right, so that means that, well, this is a different example. We go up here. If I make a date, New Year's, and it's a const object, then my print function, the only way I can call it is if I make it a const function. And then the const function is a promise that I'm not going to change the day, month, or year of that particular date object. And then inside of that, of course, I can call other functions, but only if these are also const, right? I cannot call any non-const functions from a const function. And then talked about last class was constant parameters, which, again, in this case, I have a student, and they have a student number, and that student number, your student number is going to stay with you for the rest of your life. So in this case, maybe there's no point in changing it. Well, if I do make a const parameter, the one thing I do have to do is I have to use, again, member initializer syntax. It has to be initialized right away, right? Before my call to or before the student constructor runs, the constructor for this string object must run, and I have to give it a value. And then the other consequence is that, well, the compiler sort of goes, well, you used to be able to get an assignment operator for free. It just does a byte for byte copy, but now this gets deleted, right? The compiler says, well, I don't know how to copy one student number to another student number since they're both const. So I give up. It's up to you. If you want to implement this, that's fine, you can. But the compiler will take away the one that you get for free because it no longer works. And that's about where we left off. Questions so far? Okay. So to continue this talk is, well, the third main place that we worry about const is the const parameter. Incidentally, you can do this if you like. There's nowhere in the assignments where I expect you to do this, right? As mentioned, there is sort of a philosophy or a line of arguments that says, don't make const parameters, or sorry, don't make const members. They're just a pain. If you make them private, nobody can change them anyway, right? So you have the power to control who gets to change it just by using private. And so it's up to you guys if you want to, make something const in your assignment or whatever. I fully support that, but there's no need. I fall on the side of this is just a pain, right? Because now you have to rewrite the assignment operator, and well, maybe there's a use case for it, but certainly there's a lot of cases where this just creates a lot of problems. Anyway, as mentioned before, everything is context dependent. So, all right. So the next thing we're going to talk about is const parameters. Right. So when we pass in parameters, so we're going to start by talking about strings, because strings, there is this, sorry. Let's review member initializer syntax. So it is used between the constructor parameter list and the body of a constructor. You can use it, you can use it to initialize any data member, right? And it is the most efficient way to do it, right? So there's probably some compiler optimizations that happen when you do it the other way, but if you want to be sure, the member initializer syntax is the best way to initialize your member variables. You can use them to initialize any data members, but if you have a constant data member, it must be used there. And if you have an object that does not have a default constructor, then you must also use this member initializer syntax there. Okay. So, and if you use all, if you use it for everyone, then you get an empty body for your constructor, and that's perfectly fine. Right? You see that quite a bit, actually. All right, so constant parameters. So one of the things that we tell you is you should always pass by reference or by pointer, not by value, whenever possible. By default, that should be your default. Sometimes you want to pass by value for very specific reasons, but and up until now, we've been saying on your assignments that you can pass strings by value, right? Because strings are kind of special. And the thing that we like to do with strings, which is initialize them with string literals, is sort of a special case. All right, so we'll talk about that now and see what exactly is happening. And the real problem with, I guess, string literals is that these are stored in the data segment and they are constants, right? You cannot change these. Once you declare a string literal, it's basically a global variable and it's there for the lifetime of your program. Which, that's fine, that's not a big deal, but they are const, which means that they are R values, which means that we cannot wrap them. There's certain rules that we have to abide when we use them. Okay, so, all right, let's make a student Joe and print out Joe, and then try and improve Joe. Stu, sorry. I was looking at this. All right, so Stu. Yeah, so Stu is a student. Stu has an address. That's perfectly fine, right? So this is our address is statically allocated, and inside of the, we use the member initializer syntax as we're supposed to. For the rest of them, I just left them like this. Again, these are not such a big deal, but these definitely are. Okay, so let's say, well, I'm passing all of my strings by value here, right? So, and our rule is, I should pass by reference. So let's try that. Let's see what happens. Well, what happens is the compiler is immediately not happy with us because I have a default value here. And as mentioned, this is technically an, right? It is a const. Yeah, and so reference of type string and non-const qualified cannot be initialized with a value of type const. All right, fine. So we cannot have this situation. We'll just do the first parameter to start with. So we want this to be string and now, yeah, now it seems to work. So let's see what happens on our main. Well, in main, again, we like to pass in string literals as arguments because, well, it's just easy. I don't want to make a string called number up here and then pass it in. Incidentally, if I did that, it would work. But here what I'm saying is that, well, take this thing, take this specific string, this array of characters, and wrap it up in a string and pass it into the program. But the problem is my string is not a const, and this is. So this is a match. So in order to fix this, I am going to const this, right? So before we pass by value, because we like to pass in string literals as arguments, it makes our life easier. But of course, it doesn't work if we pass that string by reference. But if we say const string reference, then I'm telling the compiler, hey, whoops. I promise you I will not make any changes to this. And the compiler is OK with that because this is value. So all right, so now my student Stu, right, worked exactly the same as before. No change into the, to the application requirements, but it does run a little bit more efficiently. So instead of what was happening before, and even still now with the name, is that we were making a string and then copying this into the string. And then we have a string that is, it's an L value. We can make changes to it if we like. But that copying, of course, is a little bit wasteful. Whereas for the first parameter now, I'm not making any copies. I'm saying just take this string, wrap it up in a const, or take this array of characters, wrap it up in a const string, and pass it into the function, and that's fine. So this is much more efficient. And yeah, questions? All right, so up until now, we've been using passing strings by value. So we were doing this. This, of course, does not work where we do not have the const. But if we, it's a little bit sort of, I mean, it doesn't look as nice as just a plain string. There's a lot going on there. It's a little bit busy, but it is more efficient. It is the best way to do things. And so this is an assignment too. So if you pass a string, it should be by const string reference. All right. Some of you are going to forget, and then you're going to be, what would happen to all my marks? And so we put a cap on it, right? I think it's like 4 marks total for stuff like this because of the first assignment we introduced this, people miss it all the time. So if you don't want to lose those 4 marks, please apply this to your parameters. And we'll talk about another case right now. So I also have, in this case, a move to. And I'm moving to an address. I'm changing the address of my student. And of course, I'm passing it by reference as I'm supposed to. So let's we don't really need. What happened? We don't really need Joe. Okay, so I'm going to make Stu, and then I'm going to make an address. Just locally declare some address variable, and then I'm going to have Stu move to that address. And it's going to pass it in by reference, which means it's going to give a memory address to this location, essentially behind the scenes. Inside this move to function, I just apply the assignment operator, right? So this is going to take this address and it's going to do a byte for byte copy into home address. And then I'll be, my student will move to Montreal, still Main Street, I guess, but. And yeah, so Stu is originally default, I guess. We didn't give him we didn't give him an address right away, but then we moved to 23 Main Street, Montreal. Okay. But what we frequently do so here I made a separate object and then I pass that in as a parameter, and then this temporary object gets destroyed when I exit from the main. But I could be a little more efficient about it because I don't really need this thing anymore. And I could do something like this. And this temporary address object will be destroyed immediately after this call, which is slightly more efficient. Let's see, for some reason, it seems to be working. All right, well, let's compile it then. And yeah, so cannot bind a non-const L value reference of type address and to an R value of type address. So what happened is that anytime you make a temporary variable like this, it is an R value, right? This is a const, and that means I cannot make changes to it. Also, what it means is that I cannot discard the const qualifier when passing it in as a parameter, which means that in order to make this match, I have to say, well, I mean, inside my move to function, I'm not making any changes to this address, right? All I'm doing is copying it into home address. So this is a read-only situation for this address class, and so I can make a const and not affect this function whatsoever. But then the nice thing is I get to pass this in, in some sense it's similar to the string literals in that it's an R value that we pass in directly. And so yeah, this is the sort of thing that on your assignment in the test, I think I do stuff like this. If I didn't, I'll do it on the next one for sure. But this is generally how I test for this, right? I pass in, I make an R value object and I pass it in. And then if you didn't make it a const reference, this would not compile, as you saw. All right. Questions? Okay, so the last sort of instance of this that we're going to concern ourselves with today. So here, anytime I can pass in, I have to pass in my objects by reference, which is great. Or I should always pass in my objects by reference. And if I can make it const, I should do that as well. Let's do one last thing. So here I have, this is something that you might actually see. I'm going to get a student. I'm going to return it by value. And so what I want to do is make a student Joe equals get student, right? And, oh, I need an ID. Well, whatever. ID 1. It's just a dummy variable anyway. So yeah, you could see something like this at some point. Is this going to work? I'll make a liar out of me. Yeah, I think there's some compiler optimization that happens behind the scenes. Let's try this. I mean, it's funny. It's always the one thing you don't test that gets you. So let's do, this is, let's do this. Student Joe. Maybe I'm wrong. Um, I'm trying to call the copy constructor, obviously, but I'm trying to call it in a way that I just in the wrong place. Okay. Uh, so technically this is a call to the copy constructor. I guess I thought I tested it, but I guess I didn't. Apparently this works though for some reason. Which it really shouldn't. I'm not sure exactly what Joe.print. Let's do. I mean, that is one of the things I like language is that there's always something to learn. Am I just in the wrong place? Because this is a const parameter. Yeah, okay. I don't know. I'm wrong. Uh, Apparently you don't need to make this const, which is somewhat surprising. However, uh, it is generally advised. For what reason now, I don't know, because I cannot come up with an example where this breaks. I assumed that would break, I guess. I thought I tested it. But the other place you would put const typically is the copy constructor, right? So this is an instance where I'm passing a student by reference. And I am not making any changes to the incoming student. This is all read only, so I can do it like this. Although I'm a little bit surprised that works. I will look it up and get back to you about exactly what happens there. But yeah, just for the copy constructor, you should also make that a const reference, right? Because generally speaking, we're not changing the incoming at all. We're just reading it. Apparently, I don't know a use case for this, or at least the use case that I thought worked is not working. It could be. I think it's the same compiler though. I thought I tried this in my Linux and it didn't work, and now I'm on Windows and might have changed something. But anyway, questions? All right. That is the fun thing about C++. It always keeps you on your toes. All right, so now that we have all of these nice rules to encapsulate our objects and protect them, and so that our objects can work well together, of course, we have a way to break all those rules, right? So C++, their philosophy is, of course, maximum freedom to do whatever you want. And so one of the things is to violate encapsulation, so using friendship. So in general, a class may grant friendship, right? Because classes are the things with access modifiers. And when I make something a friend of my class, what I'm doing is I'm saying you can ignore those access modifiers and treat everything as public. Okay, so this would be useful for a class, right? Not so much for a function, because functions don't have access modifiers, or at least global functions don't. So a class can grant friendship to a global function, another class, or a member function of a class. And the idea is that, yeah, again, it's just give away all your rights, right? Like here, you can look at all of my private member variables. The thing about friendship, though, is that you can't take it. It has to be given to you, right? So I cannot demand to see your, I mean, that sounds terrible, but I cannot demand to see anything you deem private, but you can sort of give permission, right? So, but it's very strict. So it's not symmetric and it's not transitive. So transitive means that if A gives friendship to B and B gives friendship to C, well, it is not the case that A automatically gives friendship to C, right? It's not transitive and it is not symmetric. So if A is a friend to B or A grants friendship to B, that does not imply that B grants it back automatically, right? Both ways have to be explicit. And this really should be only used in very specific situations, right? We went to all the trouble of making encapsulation. You shouldn't just throw it away. But there are sort of places where you would use it. When you have classes that work closely together, like student and address in the example we're going to see. But there's also places where you kind of actually really do need it, like no matter what. Even to keep encapsulation, when we get to overloaded operators, you'll see that it is necessary. All right, so yeah, we can be so our class can grant friendship to a function, so a global function, and or a class. Let's just jump into this example. So I have, again, my student class changed a little bit here, but so this move to is slightly different. Instead of moving to a specific address, I'm going to pass in a city and a province, and you'll see why in a second. But otherwise, it's pretty much the same as the student class we've seen up till now, and here's the address class. And so I'm going to, do I need Joe? Yeah, so let's make Stu, make Joe, and print them both out, and then we'll do all this other stuff. Okay, so Stu address is in, I guess the format's a little bit different here. I think I indented address, which I don't really like. But Stu is in Moncton, New Brunswick, and Joe's homeless. So we're gonna try and give Joe a home. All right. So one of the things we want to do is have them move to a new city in a new province. So in this case, Stu is going to move to Vancouver, and Joe is going to move to Montreal. But we didn't pass in an address, right? We just passed in a couple strings that we want to set in our address. So in my move to function, which is currently blank, what I really want to do is something like this. Dot city equals city, or home address dot province equals province. Of course, we know that, well, these are private member variables of our address class, so I cannot access them from the student class. So of course, the immediate solution that comes to mind is, well, I'll make a setter, right? And that's valid if that works. Of course, you may not always want to have a setter, right? Like maybe for some reason, I don't want someone to be able to change, I don't want somebody to be able to change the city and the province without changing the street, for example, right? So I don't really want to make a setter for the city alone, because then somebody could, say, well, they moved to Vancouver, but they still have the old street address, right? So that might be one reason. But there might be a variety of reasons. So I don't want to use a setter, but I still want this to work. So in my address class, in my declaration, I'm going to say friend class student. Right? So I'm going to declare that the student class is a friend of my address class. And when we go in here, we can see that those arrows, so those errors go away. And yeah, I should be able to move them to their new cities. Okay, so moving the students after they move, Stu is, again, the same street, but now in Vancouver, BC. Geez, the formatting, sorry. All right, so Stu is in Vancouver, BC, and Joe, well, Joe still has no fixed address, but Joe's in Montreal, so I don't know. So we were able to do that by granting friendship from the address class to the student class. Questions? Okay. So that is class to class. We can also grant friendship to a function. So here I have a where function that takes in a student. And what I'm going to say, or what I want to have work is I'm going to student found in some whatever city they happen to be in. So home address dot city. Of course, the compiler is not happy with us. So even though even though my address class granted friendship to the student class, address is still private to this function. Okay, so I cannot access it from here. So what I'm going to do is, what am I going to do? I'm going to first start with student. So home address is private to the student class. So I'm going to say here, friend void where student reference. Right? So I just use the function definition and the friend. And if I go back here, we can see, oh, all right. So one of the little squigglies went away. I'm now able to access home address. But as mentioned, right, so even though this function is a friend of my student class, and the address is a friend of yes, student is a friend of the function, and the address is a friend of student, I do not get the transitive quality, right? So home address is still not a friend of this function. So let's go and make it a friend. Where, right? So both address and student have to explicitly say that they're a friend, and then we can access everything. Questions? Okay. So I have introduced a problem here. Oops. Student has not been declared in my address class. All right, so whenever we see something like this, and it seems like there's no errors, well, let's look at what the call was. So this was the thing it was trying to compile when it came across the error. So let's think like a compiler, and let's go to our main.cc and start reading. So we get down to here, include student.h. So we go to student.h and include address.h. So we go to address.h. And then we come down here and, of course, we say friend class student. This is what's called a weak forward reference. Okay, so we are giving some information to the compiler, and why this is weak as opposed to strong, I don't know. I guess it's a compiler decision. But so when I say this, I say friend class student, the compiler says, okay, there is this class called student, and it's a friend of address. And that's good enough for this. But when I get down to this where, for some reason, it's no longer good enough, right? So it's a weak forward reference. I need a strong forward reference. I need to tell the compiler there is a class called student. You haven't seen it yet, but it's coming. Okay? Does that make sense? All right, so at this point, the easiest thing you might think is include this. So what's going to happen? Any guesses? We haven't come across this yet. So I have my address class includes student.h, and my student class includes address.h. So let's try and compile that again. Well, I get yeah, student has not been declared still. Okay, so let's go through like a compiler again, sort of maybe a little faster, but I start reading main.cc, I read student.h. Student.h says include address.h, okay, but also I've set up these header guards. All right, so I've defined student underscore h. I go to address underscore h, it says include student underscore h. Okay, so now I go back here. I hit the header guards and I don't read it this time, right? In fact, I didn't read it the previous time either. I got to here and I stopped. So I still have not read the address or the student class. And then when I get down here as the compiler, I don't know what a student is, right? The friend is not enough. So this, where I have two headers that include each other and I have header guards, I'm going to run into this problem. Okay, so this is, we cannot have a circular reference in C++. So what we're going to do instead, does that make sense, everybody? Hopefully. If you bump into it, try and remember. We're going to just do a strong forward reference, right? So this is just, I'm saying to the compiler, there is a class called student. You haven't seen it yet, but you will see it later on. And that is enough information for the compiler to recognize this function, right? Because all it needs to know is that, well, student could be, I mean, it could be an alias for an int, right? It could be anything. But I'm telling it it's a class, and then the compiler is satisfied when it gets to here. Okay, it gets a lot more complicated if you try and call a function in your header file, which is one of the reasons why we separate header files and source files. But at this stage, this is enough information for the compiler. So now I can go make P7, and then yeah, after the move, Stu is in Vancouver and Joe is in Montreal. And oh, I didn't call where. Let's call where. To verify that this works. Okay, so where are the students? Student found in Vancouver, and the other student is found in Montreal. All right, so the most important part about that is friendship, but also this idea, you know, which you may bump into at some point. When I have two header files that reference each other, it's not going to work. You have to, one of them has to do a forward reference of the class, and then the other can include the header file. All right, questions? All right. Okay, so in this case, we used friendship to solve, well, basically we wanted student and address to work very closely together, but we didn't want to grant access to every other class, right? So if I made a setter for city and for province, that would technically work, but now everybody can set the city and the province. I only want the student to be able to do it. This does, you know, this is a high cohesion, which means that these work together. And if I make changes to one, I'll probably have to make changes to both. But yeah, sometimes that's what you want. And this is the problem with the circular references in C++. Java is no problem, right? Java, they do a pre-pass and they take care of all that. But in C++, the compiler is just very, very literal. Start here, keep reading, and then, oh, I didn't read. I don't know what a student is, so. All right, that brings us to static class members. So yeah, basically it is a member variable or function that is in service to the class instead of to an object, right? So when I make a static class member, exactly one copy of that static class member exists, and it is sort of bound to that class. And it goes in the data segment. It's technically a global variable. Can be accessed using the class name and the binary scope resolution operator, or from any object of that class. Yeah, it's a property of the class as a whole. It's shared by all instances. it must be initialized at file scope. If you don't, well, I don't know, maybe it'll prove me wrong again. But previously when I tested it, you would get an error. We'll see. And we're going to use the static keyword here, but we have to use it very specifically. So some of you, is it 4 that I asked you to make some static functions? Tutorial 4. So maybe you've already done this and discovered this, but yeah, the static keyword only goes in the header, not in the source. All right, so so we have some books, book class, and each book has an ID, right? So it's in the library somewhere and it needs some way to identify it. Other than that, we have a title and an author. And that's it. So we're going to make some books. We're going to print them out. And then we're going to talk about this ID and how it's kind of brittle the way it's written. Okay, so we have our 4 books. So I'm not sure if these are completely necessary, but we'll put them there for now. All right, so here we manually set the ID. Maybe not super reliable, right? So first of all, I have to remember which IDs I've already used and which ones I haven't. Secondly, I might be coordinating between another location. And then now not only do I have to remember the ones that I used, I have to like ask them which IDs that they've used, right? So if I have one central database between multiple locations, then this is going to cause a lot of problems. What I want to automate this. I want to just, every time I make a new book, it automatically gets the next ID. And so we're going to use a static variable to do that. Yeah, so static is the keyword, int is the type, and next ID is the name. So you might be tempted to do this. Oh, good, it didn't let me. So it says it must be a const to do this, right? Because at some point you're going to be trying to think of how you initialize it, and you're going to be trying stuff. The other thing is of course, we do not need to pass this in anymore, so let's get rid of that. And okay, so this is not, technically we want to do this. So I want to take the next ID, assign it to this ID, and then increment next ID. But at this point, I have not initialized it, right? So I wonder if this would work. Let's see, because I can sit here and tell you it won't work, and then the compiler will make a liar out of me. Right, okay, so it doesn't work. That's good. And in fact, you get some really weird, this is undefined reference to book. This is, yeah. Somehow I've managed to read some or try to write some memory that I shouldn't. All right. So I want to initialize this. Of course, this exists outside of any book object, right? So I cannot wait, I could try and do this. This is a bad idea, of course, because I'm going to reset it to 0 every time. And also, it doesn't work. So what I need to do is I need to initialize this at the file scope outside any member function of this class. And so what I'm going to do is I'm going to use the scope resolution operator. Oops. Okay, so the type is int. It belongs to the book class, and then the variable name, and then I can assign it at, because it is a global variable, so at file scope is the natural place to initialize it. And then all of this should work. And well, it starts at 0 instead of 1, but we could fix that pretty easily. Okay. All right. Questions? So that's static variables. Maybe though, and it's private, it's a private variable, like I can still use these access modifiers. The static keyword, however, only in the header, not over here. If I put static over here, well, probably it won't compile because I said it's in the book class, but the static modifier means something different here. But let's say now that I want to, inside my main function, I want to print out the next ID. So b1 dot get next ID. All right, so this doesn't actually exist, so let's write it. And this actually, since I'm returning a static, well, I could use a member function, but I'm going to make a static function that returns an int, get next ID. Again, the static keyword goes in the header. When I write the implementation, put it right here just for fun. I do not include static, right? So get ID. Okay, but I do, of course, include the scope resolution operator to tell the compiler that this belongs to the book class. Now my get next ID is going to work, and I can see what the next available ID number is. In this case, it's 5. Okay, and I did that by taking this book object and calling get next ID on it, which is fine. This is perfectly valid. I think in Java this gives you an error. Maybe I want to actually, before I make all my books, I want to find out what the next ID is. And so in this case, I don't have any book objects I can reference, but since it is a static variable, I can use the scope resolution operator to reference it, right? So if I want to access a static member function or variable, if I have the right access, but I don't have any objects, I can use the scope resolution operator. And so yeah, next ID is 1 before I make all of my objects, then I make them all, and then the next ID is 5. All right, questions? Okay, so I think that takes us to the end of encapsulation, or at least that part of encapsulation. Yeah. So static member function is a service of the class as a whole. I can only access static members in there, right? So this is, I guess, something to keep in mind. I can't say, well, I can't return ID, right? Because ID is specific to a specific object, right? It's not a static member variable. It is a regular member variable. So I can only access the static members in my static functions. I could pass in objects to a static function of the same type, right? Like I could have a static function, compare book 1 to book 2. That's totally fine. And specify the static keyword goes in the class definition, not in the source file. All right. That brings us to linked lists. Now I tried to think of something a little more interesting because I've gotten complaints in the past about linked lists. I mean, it's a great example of dynamic memory, of access modifiers, encapsulation in general. So it is a useful example, but I've had people complain that, well, you've seen linked lists. This is the third time you're seeing a linked list, right? Possibly if you did it in 1406 and then 2401. So I try to think of something else, but everything else is either way too easy or kind of pretty hard. So linked lists it is. I don't know. Sorry if you're, sorry if this is a repeat and ends up being very boring. But there are some good lessons here that touch on all of the topics that we've talked about so far. So what is the linked list? Also incidentally, so assignment 3, I will I haven't figured out the exact version of the linked list, but you'll be doing something like that, some sort of linked list implementation. So we've been talking about encapsulation, and now we're going to look at an encapsulation example. While they demonstrate many useful concepts, such as access and encapsulation, abstract interfaces, separation of data and containers, and memory management. So all of the things that we've tried to stress so far. Also, array-based collections have disadvantages. Now we're getting into sort of the philosophical debate, and philosophically, probably array-based collections are better in many, many circumstances. But that doesn't mean that linked lists are completely useless. But we'll talk about some of the strengths. And one of them is that array-based lists, when I run out of space, I have to resize. And this is not super complicated, but it can really slow things down in the moment. Whereas, or if I add or remove from the middle of a linked list or an array-based collection, A, B, C, D, F, G. If I want to insert E, then I have to move stuff out of the way, right? If I want to keep my alphabetical order. So they're inefficient in a lot of ways, but they are array-based lists do play very well with cached memory, which is one of their big advantages. We'll see, actually. We'll profile them later. But linked lists look a little something like this. So rather than having everything contiguous in memory, I am going to have my data basically wherever in memory, and then pointers that connect them. All right. So how do we link this data together? How do we accomplish these standard operations? And how do we do things like manage access and memory as we do them? All right. So advantages of linked lists: we allocate only memory we need. If you happen to have an access to, so going back to here, if I happen to have a reference to this node, then I can add and remove pretty easily at that location in my linked list. That can happen very quickly. Access can be slower. Data is not contiguous. So if I have an array, right, I can just use pointer arithmetic and say, we'll just jump to here. But in a linked list, of course, I have to walk through and follow the pointers. I cannot just jump to a certain index. So as a result, since they both have strengths and weaknesses, a lot of times they can be combined to sort of take advantage of both of those things. All right, so linked list, we have our list class and we have our data class. And of course, it's not quite that simple. We don't want to modify the data class. I mean, technically, we could make a student class and add a next pointer to it. And then we can make a linked list of students, right? But as we talked about, we sort of want to separate classes into their categories. We don't want we don't want the student class to have a bunch of collection code in it, right? We want student class to have students code in it, and then our collection classes to have the collection code. And then we want to sort of, have that nice delineation between the two. So in order to facilitate that, we have the node class, which acts as sort of a go-between between our data and our list. All right, so our linked list class is going to look like this. We're going to do the singly linked list example. And possibly I'll ask you to do the doubly linked list on your next assignment. Unless I could think of something kind of cooler than that, but probably that's what we'll do. The singly linked list, this is my list class here, and in it there's a head, and it's a pointer to a node, and the node has a pointer to the data, which is student, and then also a pointer to the next node in the linked list, right? So the node is known as a wrapper class. It forms an abstract interface between our list and our data. For us, when we reach the end of the list, the next will point to null or null pointer, right? So that's how we know we're at the end of the list. which means that, and I should update these slides. We're going to use null pointer. You can use either, but we're going to have to be very careful to always assign dangling pointers to null. All right, so that if we don't, then we could end up in the situation where we run off the end of the linked list and into memory that isn't ours and have all sorts of undefined behavior. Okay. So yeah, why do we need this wrapper class? Well, again, I mentioned this earlier, but if we include the pointers in the student class, then students are like concerned now with data stuff. And also that means they can only be in one list, right? So if I wanted my students to be in two lists and I put the next pointer directly in my student class, then I would need to put two next pointers there. And if I wanted three lists, I'd have to put three next pointers. So that's not good abstraction. Every time I want to add them to a list, I'd have to make changes to the student class, which is just nonsense, right? So we make a list class and we have a node class that is sort of the intermediate. And right, what are we going to use as functions? Well, we have some array-based classes that yeah, I gave to you, I think. Yeah, anyway, we have an example of it. We have an array-based class that has add, remove, and all of those things, and we're just going to basically use the same thing, same interface, right? This is good abstraction. And then, yeah, so our interface will look something like this. And so we have an array-based student collection, and we're going to change the back implementation to a linked list and keep all of the same interface. And it's going to behave exactly the same. The performance will be a little different, but yeah, so this is good abstraction. All right, so we have our node class. It's a recursive data structure, and we're going to make these member variables public, as you will see why in a second. But basically, I have a pointer to my student data and a pointer to my next node. This is, I'm hard coding students in there because we have not gotten to templates yet. When we get to templates, we can make a templated version of this, but for now, this will just be strictly for students. Yeah, all right. Yeah. I don't really like the order I did this in, but that's all right. So linked lists in general may consist of a sequence of nodes with pointers to the next data, or pointers to the data, pointers to the next, possibly pointers to the previous if we use a doubly linked list. It can include a head pointer, or it should include a head pointer, but also a tail pointer, right? That can be useful for adding at the back of a linked list. It can also have dummy nodes, right? If you've taken 2402, you've probably seen most of these things. So what we're going to do, our node class, we want to be private to our list, right? We need to define this type, but we really don't want anybody else to be using. We don't want somebody to hand me a node that I can insert into my list unless I've explicitly decided they should. But in general, like I just want whoever's using my list class should be looking at this, and this is all the information they need. So the list class is going to be private. And so what we're going to do is we're going to declare it inside of our class. Default, it's going to be private, which means that no one outside of the list class can see the node class. But because these are public, I can access them from inside the list. Okay, so now I have this, I have a class within another class, which is fine, but now this class cannot be seen by anybody else, which is also exactly what I want. And then I can declare the type for my head pointer. That's what I forgot. I'll finish off this introduction to linked lists, and then I forgot the woo clap. So we'll do the woo clap after this. Yeah, so node is a private class within the list class. We can make the members public. I could have made this a struct as well, but same thing. All right, so that's it. So this is our list class. I'm going to quickly do, sorry to jump around like this, but I do want to continue with our woo clap. Okay, so we have an array. I called it array.h. It's just basically a student array. It has this public interface that we're going to borrow for our list class. But behind the scenes, it has an array. It's a dynamically allocated array of student pointers and all of the things that go along with it, right? So memory management and being a student and well, whatever. So we don't really care about this code now. We're going to throw away this implementation. We're going to make a new implementation with our list class. So class list, and then inside we will have a class called node. Public. I guess that's probably doesn't matter which order I do this in, but let's do student first and node next. And then, well, what forms the rest of this interface is this. We're going to make a couple of minor changes because, well, as we'll see in a second, there are some justified decisions. Okay, so yeah. This get size, so we can implement it. It's going to be a little more complicated with a linked list. But yeah, this is basically what I want my class to look like. I have this private node. I've stolen the interface from my array-based data structure that I know works. And here I'm going to have a pointer to the head of the list. Okay. So now before we get into the implementation of that, let's do a little bit of WooClap review. Now this might be, we'll see how difficult this is too. It might be hard to parse, right? So I have some classes that are working together, but we'll see. Doesn't matter. Again, this is just try your best. It's not about getting it right. It's about participation. For you guys, what's the dreaded midterm this week? Is there one that's sort of everybody's, or is it just all of them? Have midterms this week? Yeah. All right. Let's consider the following class declarations. Again, if you need any explanation, yeah, there will be some sort of bonus marks for the woo claps. So please try to sign in with your actual name instead of, it looks like there's an anonymous way to sign in. So I have a class A. It has a constructor. There's no default arguments here. This is just the header. And then my class B, which has a private member A. And so what of these, I'm going to show you some constructors and what should, right? So I have a statically allocated member A that I need to initialize. So what would be an acceptable way to do that? Which of these would work? I guess I had the results turned on every other time I did this, and now I somehow accidentally turned them off, which is what I actually wanted. But yeah. So the problem is I have an object A inside my or a class A inside my class B statically allocated, but I got to initialize it. Right? There's no default constructor for my class A. This is a tricky one. But yeah, so the specific problem is that A does not have a default constructor. So I cannot, it has to be initialized before I even enter the constructor block of B. A has to be given an argument, right? So how do we do that? With the member initializer syntax, and specifically this one, right? Again, I get that it's not that easy to parse when it's all sort of just A's and B's, and there's no real context there, but yeah, it would be this one. So I'm going to there's a member variable, small a, inside my B class, and I have to initialize it before I even enter into so I use the member initializer syntax to initialize it. All right, questions? All right. So which of these copy constructors? So here the problem is I have a pointer to a member A now. So it's not statically allocated anymore. So A is going to be dynamically allocated, right? So, that means inside my constructor for B, I'm going to say A equals new A. I guess I could have put that there. So yeah, so the default constructor, I could say A equals new A. But what about my copy constructor? What is that going to look like? If I want to do a deep copy. Right, so this is, that's acceptable for a copy constructor. Also, we could have added const in front of the internal B here. So this could have been written as B. So as far as the compiler is concerned, both of those work. And you can actually overload it. I think you can overload it. Probably. I have not tested it though. All right. Yeah. So it looks like most of you got it. So in the top case, of course, that's just a shallow copy, right? So that's going to copy the memory address, and they'll both be pointing at the same thing. This number 2 is closer, but there's no new keyword there. You need the new keyword. This would actually give you a syntax error, but probably have the right idea, but the correct one is 3. This is, it almost looks like 4 would work, except that I is private to the object A, or to the class A. So you would not have access to it in B's constructor. But that's, again, sort of close if you guess that, just minus some access. Questions? Okay. Oh, my goodness. All right, let me get this. Would this code run? Why or why not? All right, so we talked about const modifiers. basically I make an instance of A, but it's const, and then I call print on it. And so will this run? Why or why not? Assume all of the necessary includes, and using namespace standard and everything else, of course, is there. All right. Well, that's good. You guys are, yeah. I mean, that lesson sunk in, I guess. So yes, the answer is 2. You can only call a const function on a const object. So print is not const, even though it doesn't actually modify the member variable. I need the compiler needs guarantees, and it doesn't have it there. Okay, questions? Do I have one more? Which of these constructor implementations would work? So again, I have a class A. Here is my constructor declaration. It takes an int I. That int is const. So which constructor implementation would work? Assume there's only one. Again, the problem is that yeah, I is a constant. So it's a constant member variable, which means that, what did I do here? Let me see the definition. And it's statically allocated. So yeah, let's talk about 3. Unfortunately, it is a statically allocated member variable. So new returns a pointer. I is not a pointer, so that would not work. Although it's the right idea, right? It's member initializer syntax. This, of course, I've not called that, I've not initialized I soon enough. It has to be initialized before I even enter that function. So it is, in fact, 1. So I use the member initializer syntax and initialize I right away. And then it keeps that value forever. Questions? Okay, I think that's it. Do I have more? Okay. All right, so we have 5 minutes left. So we've made our list interface, our list header, and now we're going to make the list body, but we're going to first talk about how exactly to do that. So this is one of those cases where, you know, if you're stuck, drawing some pictures is going to help quite a bit. But this is the linked list that we're going to make. So we are only going to have the head. We're not going to worry about the tail. We're not going to worry about previous, a singly linked list with the head. And we're going to write our functions. And well, at the heart of every function in a linked list is a traversal. So we're going to start with a traversal. We're going to start by writing the print function. And so what do we do for a traversal? Well, we have access to this variable. And well, we can follow the pointer. We can follow the data and say print the data, right? So, or data.print or data arrow print. And then we're going to walk and we're going to do the same thing. We're going to call print on the data. Of course, we want, if we redirect the head over here, then this gets disconnected and that first node is going to be lost forever, right? So we have to keep the head pointing at the head of the list. So we're going to make a temporary pointer
Like all my assignments are done and like
in order to do a traversal, right? And then when we want to go to the next node, we're just going to say current equals current next, right? And it'll follow this pointer, grab the next node, and we can print that out. So we've got 5 minutes. It's enough to write a print function. So my list.cc, I'm going to include list.h. Well, I guess let's write the constructor first. That's probably a good idea. So we want the head equal to null pointer, right? Extra important in this linked list class that all dangling pointers are pointed to null pointer, because this is going to be how we tell that we're at the end of the list. We'll come back to the destructor later. First, we will exactly what we should be doing there, and then we'll do it. And then, so we want to do print. So void. And again, print is just a traversal. It's a const. So we want a node that is going to be the current node, starts at the head, and then a traversal is just a while loop. And the while loop is while so while the current is not equal to null pointer, again, null pointer is the universal indicator for we're at the end of the list. So while we're not at the end of the list, well, the first thing is make sure we go to the next node. But in the meantime, current data print. Okay, so that's, we don't have anything in our list yet, so we don't have any way to test this just yet, but you know, this is the heart of everything we do in a linked list is this traversal, this little while loop. And we're going to introduce other variables like previous and things to keep track of where we are. But yeah, and then, you know, we might stop once we get to where once we found what we're looking for, but this is the heart of everything. All right, we'll stop there for today. Next class, we will continue with the linked list stuff. Again, if you are tired of linked lists, my apologies. But there are some good lessons here. And yeah, so don't forget your tutorial 5, and good luck on your midterms.
Like the release of the midterm part?
Yeah, end of this week is where we're aiming for. So yeah.